Okay, indeed, it's my great honor and also a great pleasure to introduce our speaker today, and Professor Malcolm Bolton. And I guess most of you know him already, but just in case I can see some new faces, and you may not know him well enough, and I just give a very quick introduction of Malcolm. Malcolm got his first degree from Cambridge in 1967. And before most of you were born, I guess, okay? And then he went on to study a master's degree, not in geotechnical, in structural engineering, okay? By surprise, I just talked to him earlier on, because at that time he got almost full mark in structural engineering. That's why he went to do a PhD, with intention to do a PhD in structural engineering. And then later on he found it so boring, then he switched to geotechnical. And I'm sure he will tell you more about his story. By the way, and then he got a PhD from Cambridge later on. And so happens he met Professor Schofield and just bumped into each other. Okay, and then he was converted to geotechnical in 1979, I believe, or 69. And ever since, and he was sort of recruited to geotechnical field. And obviously, we all know that he published so many papers and won many awards. In particular, one his classic paper. And some of my students know that in some way I forced them to read your paper in 1986. Okay, Dilatancy. Okay, it's one of the recommended reading paper in my research group. And he gave a ranking lecture in 2012, and also gave the first Schofield lecture on physical modeling. And he's a fellow of Royal Academy of Engineering, and also he has won so many awards. And I'm sure from the website you can find those information. And actually, and I'm not going to occupy any more time for Malcolm. So will you please join me to invite Professor Malcolm Bolton to give us a distinguished lecture.
It's a great pleasure to be back here at UST and giving another one of these talks. Of course, the danger of inviting retired academics is that they have nothing new to say. And in a way, I feel like that. But looking back at the work that my research group has been doing this last 45 years or so, I do keep seeing new threads in it. And I hope I've picked out some new threads that I can show you this evening. And so the topic echoes that 1986 paper that Charles kindly mentioned, which is called The Strength and Dilatancy of Sands. And in this talk, I'm going to throw in the data of clays, or some data of clays, having shown or reminded you how I dealt with sands 30-odd years ago. So I'll throw in clays and rocks. And that's why I hope I can get away with the title of Strength and Dilatancy of Geomaterials. I'm going to tell you or remind you that the typical code approach of defining an ultimate limit state as a once-only event has its flaws, and that's the bullet point on cyclic softening by dilation. I've only got an hour and a bit, so I haven't got time to show you anything on clay slopes, but you can ask me about that at the end, if you wish. And then I'm going to emphasize some points on decision-making with respect to classes of problems that either are vulnerable to cyclic softening or not. And we'll do that. And then I've got some sort of policy issues at the end that here I've called principles of design. So that's where we're going. Okay, and IAS lectures used to invite people from any field, but as I look round the room, I feel I probably know almost everybody. Are there any sort of fugitive physicists or mechanical engineers, chemical engineers? No. I put this slide in case there were, because when I gave my first IAS lecture, there were only a sprinkling of civil engineers, and there were a lot of sort of multicultural mechanical engineers trying to learn something. So you know where soil comes from, and it's all to do with slippage either of grains or blocks, is, for example, the failure of slopes under dead weight. And then in addition, you've got earthquakes. You've got certainly pore pressures, which I'm not going to spend any time talking about. This isn't a lecture specifically on slopes. Otherwise, I don't think I would be able to get away with not mentioning the sort of hydrogeology, the water flow that kills slopes almost without exception. So most of what you're going to get is the bullet point that warns you about it. You guys also know about effective stress. I point out right at the top there that soil isn't a continuum. You need a representative elementary volume. I always think that if you were doing sugar mechanics, you shouldn't be thinking about a single grain of sugar. You should be thinking about an agglomeration of crystals about the size of a sugar cube. That might be 10 by 10 by 10, 1,000 grains. Might be statistically representative, that you've got enough patterns of contacts between the grains to capture the essential behavior. In soil mechanics, we assume that's not a problem, that we can imagine a point being a sand cube, like a sugar cube, and even the sugar cube is much smaller than the boundary value problem we're trying to get an insight on. So we don't have to think very hard about it. They have to think in rock mechanics much more carefully about the meaning of stress and the magnitude of stress, because they're the wrong side of the REV argument. It's by no means clear what the scale effects are. And if anyone's interested in that, you can ask me a question on that at the end, because I'm not going to say any more about it otherwise, I don't think. So we know about Terzaghi's principle of effective stress. And I just wanted a picture that reminds us all of the interlocking between grains or blocks. And to my shame, I couldn't find one of my own pictures of sand. And so I downloaded from geology.com the picture of sand on the left. But we know what sand looks like. But I just wanted to remind everybody of how interlocked a sand aggregate is. And then clay in an SEM, you always go to Pierre Delage for the nice SEM pictures. Clay is sort of similar. It's interlocked groups of grains formed of platelets. So the platelets are sort of equivalent maybe to the asperity on the sand particles, but it is thought that units of kinematically similar clay vectors would group around an agglomeration of clay platelets, like big crushable grains. And then rock joints, of course, this is taken out of one of Nick Barton's papers at the bottom. is again a little bit interlocked. And this is the context of most of the lecture, the interlocking between grains and blocks. So what you've got is that shear can't take place on any internal surface without creating a disturbance in the fabric, which in some instances would cause dilation, change of volume of the whole sample at its boundaries, and in other cases would just cause sort of juddering, statistically. Or crushing, which was a feature of that 1986 paper and is going to be a feature of the next slides as well. Kenichi will be irritated to see this slide because he doesn't like it. And I know why he doesn't like it. What it's trying to show is that if you try and shear soil or rock, analytically, you'll be thinking of some shear directions, maybe not a crude slip surface, but some sort of zero extension lines or some attempt to shear in some direction. And what this is reminding us is that a representative interlock shown here between two lumps that are traveling in different directions because they're embedded in the upper and lower part. You can think of it as a direct shear test if you want. And this is a representative sand grain or rock joint or whatever you want. And the contact plane is at an angle psi to the macro slip plane. I've got the black plane as macro. I've got the red contact surface as micro. And so when you push the top block, it can't go horizontally unless there's crushing. Otherwise, it has to override at an angle psi. And we've got used to calling that the angle of dilation. So the way all this developed, I was in Manchester doing structures while Peter Rowe was a professor of soil mechanics. He did stress-dilatancy theory, and he started calling phi mu the angle of friction associated with the coefficient of friction mu between two smooth surfaces. And in Manchester and at Imperial College and various places, they started trying to measure what mu was between two smooth pieces of quartz and got various estimates like 20 degrees. But the angle of friction of sand is much bigger than 20 degrees. And so Rowe got interested in dilation. And this is either showing or reminding you that the interlock here with its angle psi throws out the normal to the actual plane of sliding by being psi from the vertical here, just as it was psi from the horizontal on the macro plane of sliding. And then in addition, the actual force resultant would be at an angle phi mu to that, to explain that it can slide on that red micro plane. And then Coulomb, standing back and looking at the inclination of the force through the macro plane of sliding, would call that the angle of friction. And only if we get to realize that it's not really friction, that this is geometrical, it's dilation, would we hesitate to call that anymore the angle of friction. otherwise you would be saying friction equals friction plus dilation, which might linguistically seems a bit challenging. So angle of shearing resistance would be a better thing to call it. And that's a sort of secant phi value if the interlocks don't crush. Rowe had a lot of trouble with phi mu and phi crit in his own stress-dilatancy theory. And if he'd known what the latest research, and I have no reason to second-guess Senetakis, Matthew Coop, Tedisco, Sorzan foundations showing that phi mu is probably of the order of 10 degrees between smooth pieces of quartz. So when sand actually slides on sand, 10 degrees. So anything bigger than that, you need to explain what's going on. And so what's particularly demanding is consider phi crit. Let me look back for you at the definition of phi mu. That was a single crystal or a single element sliding against another element. Now, phi crit is the angle of friction you measure, for example, in a direct shear apparatus, when an upper box of sand grains, for example, slides over a lower box. So in this case, statistically, the grains are going up and down. And it's a much larger number. So even when dilatancy is 0, you've got this critical state phi that might be 32 degrees for smooth quartz sand, rounded grains of a given size, would be higher if there was a dispersion of sand sizes, but they were still sort of smooth, sub-rounded, but much larger if you had dispersed sizes and angular fragments. And that's just the critical state bit. 40, 36, 32 plays 10. And that's why Kenichi didn't like the earlier slide. I mean, he can come back at me at the end, because there's obviously something else going on. I'm not talking about dilatancy here. I'm talking about the critical state angle. So, can we get anywhere on what is the physical basis of phi crit? And if we can, does it matter? So I'm restating the problem. Everyone finds that they've got to write phi equals phi crit plus psi. So if there's no dilation, the box of sand isn't changing in volume when you shear it, and that's the definition of a critical state. So you feel impelled to write critical state phi. And it's those bigger angles that I was talking about. So what's the explanation for such a big angle if quartz has this small angle of friction? So it's hard to summarize, but I've tried in one bullet point, because it's all the space I've got. Maybe it's the statistical nature of the contacts and the way they're organized. So what I chose to put here is that grains surrounding collapsing voids, you're at a critical state. Some voids will be getting bigger, some will be getting smaller. Some contacts are sort of collapsing, some are jamming and are persistent. And the thought is that the ones that are jamming and persistent carry large forces, and the ones that are collapsing don't carry any forces at all. So it's very undemocratic. So even though volume is constant, the soil behaves mechanically as though it's sort of internally dilating, even though you can't see anything at the boundaries. That's what I've chosen to say. It's not quite enough. It's still a sort of active research topic with people doing micromechanics, looking at contact force distributions. And so it's a sort of jamming, even in soil at a critical state, which explains the extra friction that caused such a lot of trouble to Peter Rowe in the 1950s and 1960s. And the next part of the story is, as stress increases, even if you had some external dilation, that then reduces due to crushing. That was the proposition I put in that 1986 paper. And there's a lot more evidence now in favour of it. And so I need to say something about crushing. Before I do, this is the standard sort of undergraduate lecture slide on phi against shear deformation. So as you develop some phi, as you mobilize some shear expressed as a stress ratio, written as an angle of shearing resistance in degrees, you may find that dense soil is like the green line that reaches a peak secant phi value, and then it drops off, whereas a box of loose soil would painfully climb with a lot of shear strain to the same phi value. Phi crit is a material property. Rather strangely, in a way, it means that even if there's crushing, thinking of all the states that soil can get into, that jamming between interlocked particles at a critical state must be constant. Otherwise, you wouldn't see constant critical state angle. It's sort of intriguing. But it is universally observed. It's not quite constant, but it's a good starting proposition. And so what I've written there is it's a safe design value. If you were a structural engineer and you didn't know anything much about what these axes were, you might think that this was stress and this was strain, and that's an upper yield point and a lower yield point. And all structural engineers after the Second World War agreed that nothing should be brittle in design. And so they decided not to design to upper yield points. And unfortunately, the people who we think of as the great-grandfathers of soil mechanics didn't have that wisdom and decided to pivot all their thinking about peak strength, which is brittle. And that's part of the theme of the talk. The importance of dilation, which creates this peak, or negative dilation, which slows down the acquisition of critical state phi, means that you want some sort of index to understand how much dilation you will get, positive or negative. And we'll see in a moment a definition for a relative dilatancy index, which is pretty well what I described in 1986. And looking down here, this is just a reminder that the dense soil is getting looser, is softening, and the loose soil gets denser, and they both end up, again, experimentally observed at a unique critical voids ratio. It's not a universal truth, but most soils are polite enough to show you that result. So there are these little bits of uniqueness that make critical state soil mechanics so valuable. It's always nice to have a proper material parameter. And so strength and dilatancy of sands. So I'm going to go through this a little bit more quickly. 1986 paper, data of 17 sands. It was all I could find at the time. I thought when I retired I would have a lot more time on my hands to do things like looking back at the 2,500 citations this paper has got and just collect together all the other sand data that people have generated since 1986, but I haven't had time to do that. But as far as I know, what people are saying is that it's a good basis for understanding all sands, or silts, just as long as they're sort of inorganic. Looking at influence of dilation on peak strength, the aspect I was just explaining, and variability of dilation with effective stress. Therefore, influence of relative density and grain crushing on dilatancy becomes important. The critical state line, which was an aspect I didn't emphasize in the 1986 paper, and maybe I should, but I can now, so I will. The non-linear envelope of peak strength, and therefore dispensing with the Moore-Coulomb equation in its linear form. That's where we're going. So, typical Cambridge-style graph, voids ratio against logarithm of mean effective stress. You start off in the laboratory playing with sands, doing maximum density, minimum density, E min and E max, and marking out an initial position using relative density on a scale from 1 to 0 on that blue arrow at about 1 kilopascal of mean effective stress. And of course, if you increase, looking at the horizontal axis, I've got more than 10 cycles, natural cycles, mind you, of logarithm on the base. So I'm going all the way from 1 kilopascal to 20 megapascals. And as we know, what happens is the loose blue sand contracts down some line and then goes straight after a point and reaches its normal compression line, as we call it. The dense sand does something similar, obviously less compressible, but then it joins the same normal compression line. Not universally, but very often. With a critical state line, which in this linear region here is about 1 unit of logarithms, natural logarithms, to the left. And so what you've got is that loose sand contracts under shear even at low stresses. Dense sand dilates under shear at low stresses, but contracts at high stresses. Here it is doing it. And so you need not only relative density, which you can judge at 1 kilopascal in the laboratory and quote, but also you need relative stress. And so I need a parameter, and I called it P-C, a sort of crushing stress, sometimes sigma C, which is very roughly the point at which the dense and the loose sand converge on their unique normal compression line. Just with a broad brush. And so you need a relative density and a relative stress in order to be able to predict dilatancy in this moderate stress range in the body of the diagram here. I'm not going to talk at all about very high stresses down here, just the way the critical state line sweeps across this diagram, causing completely different degrees of dilatancy. If you move up and down, that's relative density, or if you move from side to side, that's sort of relative crushability. So relative density, we are all geotechnical here, so I don't need to tell you what it is, but there it is. And strength correlations work best with relative density because it links best with the idea of interlocking. So you don't want absolute densities. You want to know where it is on that vertical scale. But that's not all. You need relative crushability. And here I've swapped back to sigma dash C, thinking of direct shear tests again. It's actually the same number, the same parameter, and the same meaning as far as I'm concerned. So that's the confining stress at which normal compression lines converge irrespective of density, roughly. But the significance here is that it's something you could call an aggregate crushing stress, because in other research that I haven't got time to talk about, it has become clear, at least to me, that the plastic strains, the permanent settlements, the permanent void ratio reductions caused by enhanced stresses are due to breakage. And the linearity of the normal compression line is a function of some clever mathematics, if you want to look at it that way, that Glenn McDowell did, partly when he was at Cambridge and much more now he's a professor at Nottingham, due to the breakage not only of grains but of the fragments that are broken grains. And so you can end up sure that these are examples of fractal compression and breakage of equal probability of breaking any element. So, crushing. So sigma dash C is some parameter, maybe as I've described it, but to be determined perhaps by shear testing, looking at how the dilatancy is wiped out at enhanced stresses. So typical values, in the 86 paper I talked about 20 megapascals for all quartz sands. That must be a gross simplification because I know there's a size effect. Large grains are weaker in proportion than small grains. We know this with regard to rods and fibres because glass fibres and carbon fibres are much stronger because the flaws in them that would give rise to brittle fracture are obviously much smaller, and so their brittle strength is greater. And so for quartz silt, as you'll see later, a much bigger value, 80 megapascals, turns out to be appropriate. And much less for broken shell fragments. And so this is my apologia about using sigma dashed as the vertical effective stress in a shear box, and sigma dash C similarly as the parameter that goes with it, which is the crushing stress. And so the relative dilatancy index, and this was me pulling together a database and trying to find any common sense in it. You have to have the density index and the stress index multiplied together and then maybe a -1. That's what I plumped for. And then I discovered that dilatancy and the brittle strength component, phi max minus phi crit, everything was proportional to IR defined in this way. So if the relative dilatancy index, this thing here, was negative, it indicated a tendency to compact, so that shearing caused the density to increase, and you end up ultimately at a critical state. And if IR is positive, that indicated dilation, so it softens and ultimately reaches the same critical state. And IR equals 0 implies you're at a critical state. So looking back at the equation, you're at IC equals 1 over ID. So the natural logarithm of sigma dash C, so you're at a critical state, so at a stress sigma dash crit is 1 over ID. So this is an equation between sigma dash crit and voids ratio, E crit. So it's the equation of the red critical state line that I showed you on the earlier slide. And approximately so it is. So these were the correlations. Peak strength component doesn't equal psi max, which is what the simple overriding model would have you believe, but presumably due to statistical reasons of the sort I was referring to, there's a 0.8 factor to get the best correlation. At least that's what I discovered. But then either of those is 5 degrees multiplied by the relative dilatancy index. In triaxial strain conditions, it's 3 IR, because you're wasting dilation in every horizontal direction. But in all conditions, the dilatancy rate defined as Peter Rowe did, rate of change of volume with axial strain in a triaxial compression test, 0.3 IR. And these came out sort of coincidentally as nice round numbers that sort of fitted the data, as I'll show you in a second. So it's sort of broadly consistent with the interlocking friction model, which is very similar to Rowe's stress-dilatancy models, but in the context of simple shear. And as stresses increase towards sigma dash C, grains break, the volume reduces, and therefore you reduce the dilatancy and end up on the normal compression line. So that's well known to all of you. And the data of the sands fitted, so 6 sands in the literature with a relative density of 80%, fitted between these, all these lines on here are the correlations I've just shown you. This is a plot, obviously, of the dilatancy contribution, delta phi, phi max minus phi crit, against log p dashed. So if you look back at the basic equation, these are straight lines. These are the predictions, the data for 50% and 80% within a couple of degrees. So that's okay, or seemed okay. Here's the dilatancy rate in plane strain and triaxial strain against relative density, all at 300 kilopascals or thereabout. So that's why I thought that. The black line is the equation. The two black lines are the two equations, one of them 5 degrees in plane strain, the other 3 degrees in triaxial strain. That's all the sands tested anywhere near 300 kilopascals. So that was okay. This was Berlin sand, where there was data of various mean effective stresses. These were nice constant P' tests. So you could actually plot a decent diagram. So this is delta phi, the dilatant bit, against relative density. These straight lines are the simple correlations, and the data obligingly fitted within a degree, actually, in that case, I think. So, where are we with soil mechanics? What does this show us? If somebody comes along in a consultancy office and says, you know, I've found a single shear box test on this material, and there is its plot on torus sigma dashed axes, what can I say? Probably the critical state line wouldn't be here. Phi crit is so incredibly cheap and easy to find. And so that's part of the message, that we ought to do that on any granular material. First question, what is phi crit? But suppose that's not there, then if this is a young graduate, their boss would immediately say, well, you can't do anything with that. Do another couple of tests at different stresses. Put a straight line through. And we call that the more Coulomb strength envelope. So, suppose they overindulge themselves and do many tests. I remember what I wanted to point out. Of course, what's going on is that as the stress reduces, there is more dilatancy, but not as much as a linear envelope would suggest. And this can be, anyone who's played around with this knows that in slope stability problems, a little bit of true cohesion transforms the safety situation out of all recognition. It's also true in shallow foundations, by the way. So it may look on this diagram as though there isn't a huge issue, but that can have the most significant consequences. So that's the sort of thing that goes on at the moment. And then, of course, at high stresses, any given line would fall below the critical state line and give you an underestimate. So I think that is a fair statement of the conventional state of affairs. So C' is the true cohesion intercept. It is a silly name because we know dry sand is cohesionless. And indeed it is true. At the origin there is no intercept. And there's a better characterization, which is the one I've just given you. So start again. This is a new world that we've woken up to, in which people do measure the critical state angle of friction, because it is the cheapest thing you can possibly measure. So they know that, and then the graduate comes along and says, I've got this one test other than the critical state. what can I tell from that? Well, what it's given you is phi max. So what can you tell from that? Well, a lot, because you substitute phi max and phi crit into our equation. If you believe Bolton 1986 and you know you're testing a quartz sand, you might trust your luck that you know that sigma dash C is 20 megapascals. You shouldn't trust Bolton 86 in that respect, of course. You should do more tests and determine it. But if that was 20 megapascals, you could have predicted what phi max was. But now you know phi max, and if you know phi crit, you don't have to trust Bolton 1986, because this is an equation that tells you what the local estimate of sigma dash C is. I'm assuming you know what density you did the test at. So you get immediately one estimate of sigma dash C. Is it anything like 20 megapascals? And so you gain confidence. Perhaps it is 20 megapascals. Perhaps you think, oh, that's rather good. I can predict now the other nearby strengths. And so you use the same red equation to predict the strength at higher or lower stresses. Because you've measured the critical state angle, you know that if you go beyond here, you don't fall below that point. You just have to do a lot of strain hardening to get it to that point. And so you very early on gain a lot of confidence in what you're doing, and it's fundamental confidence in the mechanics of what's going on in the soil. Having plotted either your data or using my correlation in the database, you might think, well, that was a bit of a rigmarole going through the secant phi thing. Perhaps I'd like to just fit a curve to that peak strength data. And let me just remind you, this comes from real data from highly respected sources. It cuts out below about 30 kPa. People often don't do tests. And so just in that region, we don't usually have data. I've very rarely seen anything, I believe, below 30 kilopascals. But with that caveat, what I discover is that using this equation, creating the data points and then curve fitting, the data fits a power curve. So torr max over torr crit is sigma dashed over sigma dash crit to some power beta, which is quite close to being 1 minus 0.14 times the relative density in plane strain. So that's sort of interesting. So that maybe we shouldn't have been plotting torr against sigma and having linear, more Coulomb envelopes. Maybe we should have been plotting log torr against log sigma and then getting linear envelopes, which is what you get from a power curve. I'll remind you about that in about 3 slides' time. Okay, so there we are with sand and predicting the strength of sand. To summarize what I've said, it's better to use the triaxial equation. There was a very nice discussion by Fumio Tatsuoka to that 1986 paper in which he effectively said, you've forgotten about anisotropy. And he was pointing out that the angle of shearing resistance on bedding planes is smaller than the one you measure in a plane strain test with steeply inclined
slip surfaces. And what I spotted was that very roughly that knocks the 5 down to 3. And so it's similar to the triaxial number, but that's only very crude. Anisotropy is a pain. And if you're really interested in the impact of it, it implies you need to do a lot more testing. Just another thing to point out, usually you have to iterate on one. Maybe you guess what the phi max will be, the secant angle, peak strength, and then you solve the problem, bearing capacity, slope stability, retaining walls, and you find other different stresses. But now those different stresses, using this equation, feed back to different phi values. So you've got to iterate. 1 or 2 iterations is enough. I did my master's in structures on a supercomputer of its day that had a core store of 32K. So my washing machine has more capacity than the supercomputer at Manchester in those days. And our tablets can handle this sort of iteration just in goal seeking on Excel spreadsheet or something. So we mustn't let that put us off. So that's how you should back analyze failures. Try and find the density of the soil as it is, come up with a solution to the boundary value problem that you're worrying about that's happened, iterate on stress, get the right phi value, and then you should be able to understand what's happened. However, as I will show you in a moment, unconfined soils dilate prior to shear, prior to failure. Before you get to peak strength, they've started dilating. And if you keep revisiting that prior to failure point, they'll keep dilating, causing progressive failure. And that's important. Clays. How am I doing? Oh, frightening. 5:57. Got nowhere. Clays consist not so much of platelets, but of booklets or chains of particles interlocked in the way I've described. Clay mud is compressed, and these things break, crush effectively, delaminate and break up. And so clay quickly finds its normal or plastic or clastic compression line, whereas at sand we had to go all the way to 20 megapascals. If we let the clay off and reduce the stress by the yield stress ratio or over-consolidation ratio, more usually, then on that unloading, reloading cycle, it's quasi-elastic. Not perfectly, but approximately. But wherever you are, having over-consolidated it, you can get the structure to destabilize again and to start crushing once again if you increase deviatoric stress. And so you've got the same syndrome with OCR as with relative stress for the sands that I was describing a little bit before. On the normal compression line, OCR is 1 and it's crushing. And as OCR increases to a large number, you're further and further away from the agglomerate of particles initially crushing. So you've got to push it further before it breaks. And as we all know, For small overconsolidation ratios less than 2, the net result is contraction. For overconsolidation ratios greater than 3, it's dilation. So there are these two opposing tendencies for destabilization and repacking at small OCRs and the tendency to dilate at high OCRs. As we are reminded here, so this is Ishe, Hattab and Ishe, 2004, and normal compression of clay, elastic unloading. Obviously, it's an E log P plot. So, obviously, contraction from the normal compression or low OCR states, and dilation at high OCR. So this is kaolin, all pre-consolidated to a megapascal, allowed to swell back, and that is just a standard unit of teaching at Cambridge and possibly here as well, though I haven't asked Charles, but I'm sure it's here as well. And so I'm using OCR, going to use OCR as an index of crushability, controlling dilation, analogous to my relative crushing index, IC. So nothing new there, other than associating the word crushing with what goes on. And that's sort of hypothetical. You can't see what clay is doing. You can see sand breaking and damaging, but we haven't got the killer experiment yet that shows blocks, groups of clay particles breaking up at different stress levels and dilating. It'd be a nice thing to see. Anyway, here's the data of John Atkinson, to who you go for nice data on clays. And there, this is the similar plot of, in this case, clay pre-consolidated, I think, to 200 kPa. Can't quite remember now. But anyway, here is the data of critical states, which are the post-softening data. Here's the peak strength data, and he puts a curve through it, and then, for some reason, wanted to draw a linear Moore Coulomb envelope, but then drew a 3-on-1 line for tensile fracture. Well, you don't have to mess about to that extent if you just plot log Q against log P dash, which is what I ended up doing with the sand. Log shear strength against log mean effective stress. It's a power curve. It's the same sort of power curve I've just shown you for sand. So that was sands before. This is clays. So this is the peak strength, and if you push it over the peak, it softens down onto the critical state line. I think that's all I had time for on clays. Well, I sort of summarized. Okay, so Atkinson 2007 normalized against P dashed at the critical state at each new voids ratio. Well, that's a little bit clunky for what I wanted to do. So I renormalized it against P dash crit on the same elastic unloading line. And then I get very much the same equation that I showed you with the sand. And so I gave that an index beta as well. And in this case, there really was some variation from clay to clay. Because in this case, in the sand, you had no idea what the probability of fracture of the different grains was. They'd never been to such high stress before. In the clays, everything's been taken up to a high stress because we're dealing with over-consolidation ratio. So it's actually a different stress history condition than was the case in testing sands. We don't often think of testing sands through an over-consolidation cycle. I think we probably should, but we don't. And so it shouldn't be a surprise that the propensity of different clays to damage in different respects and therefore give you peak strength curves, power curves with different exponents might well be perfectly sensible. I mean, if beta equals 1, there's no peak at all. If beta was 0, it's a rectangle. So as you over-consolidate, there's no drop-off in the strength. It remembers, as it were, that you made a dry stone wall out of it at high stress. But because it's now a dry stone wall, it's completely stable when you reduce the stresses. So depending on the geometry of the fabric of the clay, the particular clay, you would expect different beta values. And I found that you could also express it in terms of a ratio of sine phi max over sine phi crit. And so there are these other expressions, any of which you can rely on, but sands and clays being really very similar in the data, and hypothetically at least, very similar in the reason for the data being very similar. Just a comment about ultimate strength of clays. Lupini, Skinner and Vaughan explained that you could get clays into a critical state if they were engaging in turbulent shear, and then you might have an angle of friction of typical clays of about 20, 21 degrees. But as we know, sliding on a polished slip surface, which for some reason we speak Swedish when we talk about polished slip surfaces, call them slickensides, with residual friction phi res, and that's about half phi crit, maybe only of the order of 10 degrees, can be as small as 6 degrees. And it's tempting, isn't it, to call that phi mu. I mean, if you can see your face in a slickenside, then you're looking at a phi mu problem, smooth surfaces sliding against each other. So maybe the difference between phi crit and phi mu. It appeals to me anyway. Rocks. Better speed up. Copying Nick Barton. Rocks are nearly always controlled by discontinuities, which are nearly always rough and interlocked. So Barton did exactly the same sort of thing that I did for sands. He talked about them being interlocked and the importance of waviness and roughness and linking to dilation mediated by crushing. So he had exactly the same set of ideas. And from the very earliest days, I know I've quoted his 2013 paper, but there's a 1985 paper and earlier papers than that, when he was talking about the complete uselessness of the Moore-Coulomb strength envelope for rocks, for joints in rocks. And so in 2013, he did that sketch where he wanted to say, in megapascals on torus sigma dashed. Intact rock might be up here, and if you were very lucky with a sort of Hook-Brown criterion, you might measure some intercept. It might give you a real tensile strength and a real shear strength at zero effective stress. But all other materials, he was talking about rocks, fractured rock, jointed rock, rock fill, non-linear strength envelopes. And so that strain of work didn't begin with Rowe's stress-dilatancy. It began with pattern, but coming up with exactly the equation I began the SANS lecture, the lecture with a phi mu plus I. That's the notion of microplanes and macroplanes that I introduced. And phi mu is the material friction angle. And then Barton came along in 1977 and said, no, it's not phi mu, it's phi crit. And you can find it by just testing the rock joints until you get a steady, sort of steady value, but there'll be a juddering. So that it will have stopped dilating, but it's noisy. And so he wrote phi r. Unfortunately, in each silo of thinking, even rock mechanics and soil mechanics people can't agree on using the same symbols for things. It's sort of a pity. So he calls it the residual friction angle. I was obviously calling it critical state angle. And he immediately linked to an index comprising a joint roughness coefficient multiplied by the logarithm of the ratio initially between the unconfined compression strength of the asperities on the rock crack divided by the current normal effective stress. So that is effectively identical to what fitted sand. So re-expressing Barton in soil mechanics terms, Tormax is sigma n dash tan phi crit plus psi was what Barton said. Psi in the case of a rock joint is r log to base 10 sigma c over sigma dashed n, the normal stress on the joint, where sigma c is the compression strength of the joint face. Well, it's identical to what fits sand. And where Barton was particularly good was they emphasized the importance of doing field tests on joints. So you find a joint and you want to discover what all this is about, and he would get you doing little tests, sliding an upper and lower part of a rock joint over each other. So you tilt until it slides, and then you back analyze and find R, or you do a shear box type test and back analyze and find R. And you get the sigma C. He emphasized the importance in rock mechanics terms of getting to know the sigma C value for the actual weathered asperities. In a broken piece of rock, you get water and oxygen available and it weathers over a period of time. And so he recommended using a Schmidt hammer to do rebound tests calibrated against the unconfined compression strength of rock so that you actually get the proper weathered value. And so he's had 30 or 40 years experience validating this identical approach that worked for sands and clays in rocks. So strength and dilatancy of granular geomaterials is all of a piece. You get at large displacements, large strains, phi crit greater than phi mu, except for polished slip surfaces where you get what we call a residual phi, which is probably the same thing as a phi mu, which obviously is much less than phi crit because of the interlocking, juddery nature, the internal strong force network being undemocratic in how it distributes stresses inside the granular material. All soils and rock joints that are sheared under confining stresses smaller than those required to crush grains or asperities exhibit an initial peak phi max greater than phi crit associated with dilatancy, unless they're very loosely packed. As effective confining stress increases, crushing increases, and both dilatancy and phi max reduce, and those equations for sands, clays, and rocks that I introduced apply. And depending what the material is, you've just got to slightly change the definitions in order to link in with the data sets that have been published. But the same ideas work in every case, and in no case should a linear Moore-Coulomb envelope be assumed. And so this was what I've been building up to. This is C.K. Lau's PhD from Cambridge that was eventually published in 2011. C.K. not only did all the work doing the tests, and as you'll see in a moment, doing the analysis, but he had to do all the work, writing it up, and then dealing as ever with the negative reviews from Geotechnique. And then a few years later, somehow getting the nervous energy back to deal with those negative reviews. Of course, it was all then reviewed fresh. And he did just a splendid job on all those things. So there's a numerical analysis of the vertical bearing capacity on sand and the experimental evidence of 1G and high G tests on this problem. So these are circular foundations on sand, some dry, some submerged, and here we go. Obviously, what we chose to do was place the evidence in the context of what every engineer thinks they know, which is NC, NQ, and N gamma. And then there's the awful problem of size effects, and I'm going to say a word about that. That's really where the PhD project started. As you'll see here, CK came to Cambridge in October, and by the middle of winter, he was washing silica flour. We found a source of silica flour, which was effectively a sort of blasting powder residue. And if you had infinite patience, as he did, and also a strong constitution, you could indeed wash this stuff through rows of dustbins, taking out the fines and the coarse fraction as appropriate, so that eventually you could produce the same grading curve as a Châtelet flint grit, identical particle shapes, identical mineralogy, 50 times the grain size. And so the silt was a 50th scale model of the sand. And so CK spent many unhappy hours achieving that fantastic result that I haven't seen repeated anywhere since for some reason. And he did his own triaxial tests at a very broad range of stresses. So there's the sand on the left and the silt on the right. And if you look at it, compare, for example, 50 degrees of angle of friction, you'll see that the silt is a little bit stronger than the sand. Does that mean we've gone wrong somewhere? Well, no, it's inevitable, because silt is stronger than sand, and so it's more dilatant, as you can see at every point. It's intriguing that engineers always think that silts are weaker than sands. I'll just leave that one with you. But there's the data of phi of this quartz mineralogy, small particles, quartz mineralogy, sand-sized particles. The green line is the correlation I showed you 20 minutes ago from that 1986 paper. And so the Châtelet flint grit has a long name, but it just behaves like a sand. It's got quite a high phi crit because it's angular. And as you saw, it's got a dispersion of particle sizes. So you would expect its critical state angle to be high. And we believed that the critical state angle of both the sand and the silt was about the same at 37.5 degrees from that triaxial data I showed you. And so he then went on to do model tests of silt and sand, geometrically similar, at a similar void ratio, very dense, actually. Bearing in mind it's angular, this is pretty well as dense as you can make it in each case. So, as I was saying, you could either regard the silt as 5 degrees stronger or as 5 times stronger. So if you look at the horizontal axis, you've got to multiply p dashed by 5 to get the same result. If you look at the vertical axis, you've got to add 5 degrees. So it's the same. So it's the same relationship between strength and dilatancy, and you can express it either way. So this is the equation we introduced half an hour ago. And so what that is, as I showed you, the nonlinear peak strength envelope. We've now established PC values for the two materials. Quartz sand, as ever, 20 megapascals. Quartz silt, 100 megapascals. If you differentiate this, of course, what you get is d phi by dp dashed is minus, the delta is the 3 degrees, times the relative density over p dashed. So this is the equation, if you want to put it that way, of the curved strength envelope. So this equation and this entire slide has sort of been in existence and available to you for the last 32 years. It's the actual equation of the peak strength envelope of granular materials. Isn't it a pity that we haven't been using it, since it fits all the data of sands, clays and rocks? Whereas linear, more Coulomb envelopes don't fit the data, and we do use it. This is why it's important. So here is CK's slide out of the theoretical paper of an axially symmetric circular foundation. There's the center line. You're pushing down. It's a 5-meter footing, a big one, like a spud can or something. Submerged, dense sand with a critical state angle, as I've said, of 37.5 degrees to go with the test data that I'll also show you in a second. And under the footing, you've got an immense stress. And so you just get the critical state angle mobilized here. What he did was he did a nice analysis, which you can read about. It's a modified Prandtl style analysis of bearing capacity failure, circular footing. And as you move out of the high stress zone, the actual secant angle that you can mobilize increases until finally, when you're on the seabed, but still in the sort of passive zone by the side of the foundation, you can mobilize an enormous angle in excess of 55 degrees. And so this is just an essential feature of the solution. You've got to be able to recognize that variation. The tests, a very quick summary, 20 tests at 1G for the NQ factor, dry or saturated, small or big, silt or sand, dry or saturated. I think I said that before. Every test quite closely fitted the Prandtl style analysis with secant phi varying. So good bearing capacity back analysis in every case. Negligible post-peak softening, at least up to a settlement to diameter ratio of 2. So you can use the peak strength. Must allow for embedment effect, Meyerhof. No grain size or container size effects. No size effects. Stress effect. Small footings, small stresses, high angles of friction, high NQ values. Meyerhof, I bet you know where that comes from. That was 1951, so it's 3 generations of saw mechanicians ago almost. But you just allow for more rotation in the fan, in the sort of passive area, according to the geometry as Meyerhof set it out. And so you can read up Meyerhof's depth effect. This is a bit exaggerated, but as the footing punches in, you get this extra component of strength due to the change of geometry. So we had to account for that. But that was a sort of professor's CK had to allow for that. Centrifuge tests, fewer of those, but enough to sort of confirm very much the same thing. Good analysis of every problem, big or small, sand or silt, no boundary effects, no softening. We could only demonstrate that as far as we could take these in the centrifuge, which was a settlement to diameter ratio of 1. No chamber effect, no grain size effect, up to a factor of 8,000, which is enough, I think. I mean, silt is a pain to work with. If you're not sure of that, ask CK afterwards. But how very valuable to have grains in a small physical model that have the right size relation to the object that you're interested in. Silts do model sands. Sands model railway ballast. So you need to just square that one away. And if you want to do more centrifuge tests on silt, I would recommend it. But you need a very good research student, very patient. So load settlement, sort of elastic looking, and then you get to N gamma, if I could put it that way, and then you additionally add a bit of Prandtl, a bit of Meyerhof depth effect, and a bit of n gamma. And plotting the n gamma parts, log to base 10 of n gamma from 2 to beyond 3. This was the silt. Of course, it's stronger than sand. This was the sand. This is the theory, happens to come out straight, according to the slipline theory with phi varying, plotted against the logarithm of 0.5 b gamma, which is what you multiply n gamma by. So all this is for relative density of 1. And just to point some things out, this is an n gamma of 200, which might be appropriate if you had sand and a 5-meter diameter footing, so that 0.5 b gamma underwater would be 25 kilopascals, if I've got my numbers right. And so then you'd have 200 as n gamma. If you had silt, you could have 600 or more. If you only had a 1-meter footing, then because the stresses are smaller under a 1-meter footing, if you have silt, you could have 1,000. If you have sand, you've got to be satisfied with a number not unlike 600 or 700. So my comment about that is that an engineer using Terzaghi and Peck, or any of the thousands of textbooks that look like Terzaghi and Peck, or lecture notes, would likely make an error greater than a factor of 3 if they were trying to do it with C-phi dashed, instead of what CK used, which is the curved strength envelope, because of the terrific range of stresses in the problem. So, lesson on vertical bearing capacity of sand is variable phi, variable delta. That was the Meyerhof effect. Notwithstanding grain size, footing size, the same analytical model worked well. So you don't have to worry about it. And it doesn't matter that silt is a bit stronger than sand, as long as you've done your own triaxial tests. Known strain softening in this problem, you're permitted to use the peak strength. So the ultimate limit state design of foundations for vertical bearing capacity look as though you can use peak strength, but you must define it properly in terms of secant phi varying with stress. Linear Moore-Coulomb description of peak strength is so crude that you're going to make factor 3 errors in all likelihood. Slopes, there's evidence of brittle softening either in sands or clays. Take, for example, the 1957 paper by Skempton on London clay, which showed you could only reliably mobilize phi crit, the critical state value, even though it's a very heavily over-consolidated clay. And I've got lined up here a test on sand, and it's now 6:33. I look to I've done what I always do, which is just talk and talk and talk. 6:33, Charles. I think this was meant to finish 3 minutes ago.
Not too bad.
Should I just shoot through and get to the conclusions? Shooting through, earthquake test by Scott Steedman, also from the 1980s. 17% earthquake. Mononobe and Akabe were quite right in a way in their analysis, at least in one respect, wedge failure behind a wall. if, as Scott Steedman did, you measure all the acceleration components, you can complete the force polygons. You can therefore begin to see the problem of how, with the earthquake input, this level down here, just as the earthquake begins to diminish, the wall movements plotted in millimeters on this axis just begin to increase dramatically. So what's happening there is that the soil is softening. You can see that just in the raw data. It must be. And here's Scott's back analysis. You can mobilize the peak strength of sand about 50 degrees for a while, but then there's very strong rapid softening to the critical state, 33 degrees, in the middle of the earthquake. A problem that is loaded recurrently, as earthquakes always are, or as slopes in the natural environment are, with their natural loading from pore pressures, especially, following different rainfall events. All those things soften in situ down to a critical state, phi. So that was the summary. Cyclic loading leaves things softening to a phi crit, just like Skempton said in 1957, just as Andy Take and I published in 2011 after centrifuge tests in an environmental chamber at Cambridge with weather variations. So summary on the shear strength of slopes. Peak strength best described with phi max. Phi max drops to phi crit due to cyclic loading as well as due to increase of stress. Two different mechanisms. Mobilization of any supercritical strength, phi mobilized greater than phi crit, involves some dilatancy and softening. And so if that keeps happening on every earthquake cycle or after every rainstorm event, bit by bit, you'll shake the soil loose, either in an earthquake or watching the deterioration of slopes in the field. And so you ought to design those sorts of things, not with the peak strength, but with the critical state strength, because that's where it ends up in the worst case. I don't have to remind this audience of the Poshan Road disaster that was said to start with small slips, opening cracks, followed by a catastrophic landslide. So the question obviously is, was it shaken loose, as it were, by the onset of slippage, and then having broken free and softened, it roared down the hillside? And so the conclusion of all this, and yes, I am pretty well there, all geomaterials are interlocked, and phi crit is bigger than the angle of friction between grains. Strength enhanced by dilation, which reduces due to crushing, also reduces due to cyclic loading. Monotonic strength of things like foundations under dead load, that's okay, and has been demonstrated in centrifuge tests, so you know where you are. Live loading has been shown in some boundary value problems to soften the soil progressively by dilating event by event, cycle by cycle, to phi crit. So what you want is to design to phi crit in the worst credible design scenario, worst rainfall event, worst earthquake, whatever. And so I thought I would have finished half an hour ago, but Here we are. And so this was going to be policy pointers for discussion. It is the very last slide. All geotechnical designs should be based on phi crit unless centrifuge tests following CK Lau and others have demonstrated that the class of loading under investigation isn't vulnerable to softening during foreseeable precursor events. Maybe HKIE should work with GEO and BD to issue guidance on the replacement of C-phi parameters by proper parameters that actually fit some data. For all Hong Kong soils, checking out what the parameters should be and how you measure them. Existing infrastructure or landforms that will remain stable in severe loading events only if you can mobilize greater than phi crit are susceptible to catastrophic brittle failures. Poshan Road, for example. They need to be monitored. When engineers started making ductile steels, at that point they realized that they'd let themselves down in a sense, making cast iron suspension bridges, and started inspecting and monitoring for crack propagation in cast iron. And maybe we owe it to ourselves to take a similar approach. That was the last slide. And I do apologize, as ever, for going on for so long. Thank you.
Maybe I just shout it out. And actually, your amount hasn't been doing too badly because we start late. And I guess we should have a couple of questions because he has been very provocative. So maybe, Professor, can you come on slide 6? Now, since he's so polite and usual Japanese style, then I will say openly, I'm going to invite him next year to be an IAS distinguished lecturer next year. Yes. So please put down in your diary. Next year he'll come back to talk about slide number 6. Any? Yes. Professor Zidong?
Thank you for very nice summarize all the rock, soil, and sand and clay, and for your dialectics theory. And look at back the last application theory by application for the bearing capacity problem. Yeah. And I look back at your original 1986 paper on the sand, the expressions. There are two coefficients. One is 5 for the plane stream problem and 3 for the triaxial. Those are two angles. Yeah. And I guess that is an empirical angle. And think about it for the real problem, for the foundation problem. It really depends on the load angle. This is one more angle, and also in practice on the fabric, and on the stress directions, the relative angle between the principal stress with this fabric. Yeah. So if I suggest one of the students work on extending, express those coefficients as a function of several angles, several factors. For example, those load angle and the fabric, relative direction of the fabric with the stress and other things. What would you suggest or comments on this?
Well, first of all, I think that was a very useful thing to do. So what you're doing there is you're assuming that you can use the same peak strength envelope, for example, for inclined loading, where we know that the failure surface is much more concentrated and shallower than the sorts of failure surfaces that CK was looking at in vertical loading. So an excellent thing to do, but remember you haven't got an experimental justification for all the observations I made. there may be softening. We know there's softening in a shear box test. That's the plot of phi rising to peak, falling to critical state. That's a shear box. That's not very different to a foundation with a lot of horizontal loading on a shallow shear surface. So before you know that you're permitted to use that, you should collaborate with somebody here doing centrifuge tests of foundations under inclined load. Because it may well soften, and that may cause you to think, it was simpler than that, I'll just use phi crit.
I can see Professor Soga got stimulated, so he's willing to join in discussion.
Malcolm, I totally agree with you on this incline loading, because I think CK Lau and you were very lucky when you were doing vertical load, so it's very difficult to create a shear band, localized shear bands.
Yes, there were no shear bands.
Yes.
We could check.
Yes, whereas if you start doing incline loading, you're much easier to generate shear band, and therefore you should design with phi crit.
But just think, somebody in Leeman's group here, just think how many citations they'd get if they just did the test we're now describing. Because, in offshore engineering, if in nowhere else, you characteristically got inclined loads. And as far as I know, there isn't an experimental demonstration yet of whether you're permitted to use peak strength. So what you need to do are inclined load tests in a centrifuge, and repeated, bearing in mind the question of dilators, death by increments of dilation, eventually leading to critical state angle. But assuming that anything comes out of that, whatever it is, that's going to have to be cited by anybody designing a foundation who takes their job seriously.
Yeah, thank you for both your suggestions. I believe Li-Ming and Zedong are going to write a GRFF proposal next year.
Right.
So you got a topic, okay? And very likely they will be the reviewer. They give 5 stars.
Yes, but then if you have a little bit of difference in density in heterogeneous condition, again, it will generate some interesting behavior as well.
You see, you got all the parameters go into your proposal, and I'm sure you'll be funded. Any other questions? Ken? We cannot have any seminar without your participation. Would you like to say something? No? Okay.
Just want to say that in practice, we have to deal with other things, such as heterogeneity and structure, geological structure. So our life is probably slightly more complicated than assuming everything homogeneous, particularly in Hong Kong.
But you might find that if softening was endemic in the problems you're interested in, as it often is in slopes, that you simply use phi crit. It's not complicated at all.
In Hong Kong, we also have bonding.
Yes, if you've got rock-like materials, but if you've got completely decomposed materials, I suppose that's an easy-peasy thing. But on the other hand, you've spent $20 billion fixing that problem, so perhaps it wasn't so easy.
Maybe with that, I think it's a nice closing for this, I would say, distinguished lecture. And I do have a suggestion, and since I'm the MC for tonight, in the sense, and it would be very nice. You come up with a unified theory for sand, clay, silt, and fracture rocks, and submit to proceedings of Royal Society. That would be a nice piece of work instead of you writing a book.
Yes.
I think that actually tonight, in some way, you already said unified theory for all this. material.
I'd like to do that.
Except the interlock, you haven't covered. It deliberately avoids.
But that's Ken's point. I think once you've got bonding, you've got bonding, then that is what you've got.
Yes.
And that puts you into a different ball game.
That's why I said stretcher rock.
Unless you take Nick Barton's point that actually it's still dominated by discontinuities, but then you have to find out.
Yes. Yeah. So I think that would be a very nice piece of
thank you. Thank you
publication. And I'm sure that will be highly cited, more than 2,000 times, I'm sure.
Okay.
Yeah. That's my humble suggestion, if you don't mind. And I'm sure you all enjoyed this very insightful presentation, and from theory to data, support by data. Okay, and I'm learning a lot. Even though when I got to Cambridge first time. So I read your paper, that was 93, although you published 86. But this is the first time I was sitting there listening to you talking about your own paper. And so then and also, I would say, solve my problem has been a long time. That's the equivalent, 5 mil equivalent to residual angle. In that sense, you can put a nicely unified theory to go with that. Yeah. Okay. Thanks for your excellent contribution to soil mechanics, and I would say even a bit moving towards raw mechanics as well. And will you please join me to thank Malcolm for his excellent presentation. Thank you.